Recordings rolling. It's Wednesday, November 12th. So we're on the last lesson of Module 5, Lesson 5, Roots and Zeros. So you guys know we're talking about x-intercepts here. So they give you a few more tips how to find x-intercepts, and once you do, how you can string a basic graph together. Right, so go over, yeah, that with you guys. You guys know Alex 5455 has been open a few days, right? And then that's due on Friday. Right, so we'll give you guys as much time as you can today to be able to work on that. I'll get you guys your module quiz on Friday. So tomorrow can be an Alex day and a review day. And then guys, keep this in mind too, is that 1 month from now, so on December 12th, your Alex 50% pie goal is due. A lot of you guys have already achieved that, but if you haven't, then start chipping away on that too. Right, so what's this lesson 5, roots and zeros? Well, right, lesson 5. Here we go. Roots and zeros. Okay. So your book mentions what's called the fundamental theorem of algebra, which says that if you have f of c and that's equal to 0, then that would be a 0. So, for example, f of 3 was 0. That would be referred to the coordinate 3 comma 0, and then that would be a 0 on the graph. Okay. Okay, so we got that. And then it says every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. Yes, complex. That also refers to imaginary numbers too. Okay. So if there are real zeros, then if you draw a graph, the graph physically crosses the x-axis. And if it does not, like if you had a parabola that was hovering above the x-axis, there could still be zeros, but they would be imaginary or complex, you could say. Right? So, but there'd be a way to find those. Right? Right. So uh, also, there's this corollary here that's interesting because a polynomial with degree n, which you guys know what that means, that's the highest power on x of some x term. Okay? So degree n has exactly n roots. Ooh, that's interesting, right? In a set of complex numbers, including repeated roots. So to give you some examples here, you guys see 2x to the 3, and then, okay, there's a string of other terms, but wouldn't this be degree 3 because it has the highest power on x is 3? So there are 3 roots. Now, they might all be real, in which case the graph would cross the x-axis 3 times. Or maybe this graph only crosses the x-axis once, and then there are 2 imaginary zeros. That could also be the case. All right, this next example, we got something to do with x to the 4, so that's degree 4, so there would be 4 roots. Again, it might be all real numbers, right? Or maybe 2 are real and 2 are imaginary, or maybe all 4 are imaginary, right? Or complex, you could say. And then x to the 5 real roots. Okay. Here, that last one, I'll draw a picture for you guys. Or draw some pictures. Okay, so let's go ahead. Get the axes going. If you have x to the power of 5 as one of the terms in your polynomial, okay, so let's get x-axis, y-axis. Okay. If I have y equals x to the power of 5 plus, and I'll just leave dot, because this equation can finish out a bunch of ways. Okay. What could that possibly look like? Well, they could go up, down, up, down, up. Okay. In fact, because if you saw this graph, you would know it would be best modeled by something to do with x to the power of 5 plus and a string of other terms. And then 1, 2, 3, 4, 5. See, there's 5 places where this crosses the x-axis. Is that okay? Or here's what you saw something like this. It goes 1, 2, 3, 4, 5, something like that. Okay. Where there's 1, 2, 3 real roots. Okay. And then this does dip down and go up again, but it doesn't actually cross the x-axis when it does. So there could be 2 more complex roots. Yes, yeah. But you see how the number of roots adds up to the degree, which in this case is 5. Okay. Or you could even get something like this. Okay. That could also, maybe if I shift this graph way up, it only has one real root, which is right here. And then, well, the other 4 roots would all be imaginary or complex. Okay, I guess that's what this corollary right here is saying. All right, what else we got? Descartes rule of signs. Descartes rule of signs says that if you write out the polynomial, so from highest degree to lowest degree. So here, I'll just teach this one by example. So if I go right down to their example right here, they have x to the 5, they have x to the 4 term, x to the 3 term, and so on all the way down, x squared, x, and then a constant. Okay. Look at the, here, let me get this to focus a little bit better. Well, or let's look at the signs on these terms. So it goes positive, negative, negative, positive, negative, positive. It's that, right? So every time that it switches sign from positive to negative, which it does there, right? Not here because negative, negative, that stays the same. So that would be a no. So your book wrote no, right? But then negative back to positive, ooh, it changes sign again. So yes, then positive, negative, yes, that's a sign change, and then negative, positive, yes. Right? So I have four yeses. You guys see there are four yeses? What that means is that there can be up to four zeros in the positive x territory, the say to the right of the y-axis. Okay? Now there might be fewer than that, but you could count two fewer at a time. So there could be up to four, but there might be two or even possibly zero if it's shifted away. Yeah.
IT, my computer's on.
Yeah.
Oh, but I have to do a moment, so I don't know if I'll make it back.
Okay. Yeah, that's okay. And then interestingly, if you look at the polynomial, not f of x, but f of negative x. So everywhere you see an x, if you plug in negative x, right, and then simplify it, right, and then also look for sign changes the same way. In this case, if you plug in negative x for x, there's only one sign change between the terms, and it's right here. Right? It goes from this negative to this positive, and everything else is that positive. Right? That tells you the possible number of x-intercepts in negative x territory. So to the left of the y-axis. Okay? In this case, there's only one, so there would be one, pretty definitively. There'd be one place where it for sure crosses the. So it might look like this, for example, right? Or something like that. Right? So here, the examples I just kind of sketched up here. Looks like this example on the top left has 3 in the negative and then 2 in the positive, counting the number of zeros. Right? This has 2 x-intercepts to the negative side and maybe 1 real in the positive, right? And then this has just 1, it's only the negative. Okay. So you can use this Descartes rule of signs. Okay? Number 21 from your book here. Of course, I have a fuller version videoed out. This is one of the ones I did. Okay? I was looking at this expression. So x to the 4 plus 7x squared plus 3x minus 9. Now, this is positive, 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 and then finally negative. So there's only one sign change from this positive to this negative. So I can say that there'd be one real positive 0. Right? So I circled that right here. Okay. Then if I say what not q of x, but what is q of negative x, and I plug in a negative x, and then I clean it up, anything raised to an even power will become positive anyway. Raised to an odd power should maintain its sign. Right? Okay, so then I clean it up and I say how many sign changes. So positive, positive, well that doesn't change. Positive to negative. Ooh, there's a sign change. And then negative, negative, well that stays the same. Right? So I have one real negative at 0. Right? So one real positive 0, one real negative 0. Guess that. Right? Now, guess yeah, there's degree 4. Well, just a few minutes ago I was saying there should be 4 total zeros. Well, if there's only one in the positive territory and one in the negative territory, okay, don't there have to be 2 additional zeros that are complex? Yeah. Yeah, imaginary. Yeah, imaginary complex. Okay. Okay. I don't remind you guys what imaginary complex is. Because what if you saw this? What if you saw y equals x squared plus 9? Okay. And you graph that. I'm just trying to remind you guys what imaginary zeros are. Okay. So x-axis, y-axis, 9's way up here. Windows create a graph that does basically like this. Okay. And it never crosses the x-axis at all. So guys, how many real zeros does this have?
None.
None. Yeah, it doesn't have any at all. Right. If you did want to factor this, there'd be a funny way to factor it. Do you guys remember how to factor this one? It's a little bit weird. It's x plus 3i, x minus 3i. You guys remember that? Where I is the square root of -1. Right? You guys seen this before. So here, if you FOIL this out, x is x squared, bing, outside, inside, cancel out. And then 3i times negative 3i is negative 9i squared, but I squared is -1, so that brings you back to positive 9. Right, so that's how it factors. Okay, so there are 2 zeros. They're just both imaginary. Okay, that's it. All right, so we've got that. Here's another example that I did in the full video. Go to this. Okay. So it looks like number 19 had this polynomial. Okay, so we got positive, negative. There's a sign change there. Negative back to positive, and then positive back to negative. So that's 3 sign changes. So you could have up to 3 positive real zeros, right? Or you might have fewer, but then you count down 2 at a time. So if you don't have 3, then there would be 1. Okay? And then if you plug in negative x, you say, well, what's f of negative x, which I did here, and then I cleaned it up. We got negative, 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 negative. All right, so all the signs are negative, which means there's no negative real zeros. Okay? Okay. And then since, guys, what's the degree on this polynomial? The degree is what? 3, see degree 3, that means there have to be 3 zeros total. Right? Now, they might all be positive real zeros. That's possible. Right? Or there could be one. Right? And if there's only one real zero, that means the other two must be imaginary. And I must have graphed this on Desmos, hence I boxed in the actual answers. Okay. So, but if you graph it on Desmos, and on the full video, I graph a bunch of these on Desmos. Okay. What else we got here? This is complex conjugates theorem says that a plus bi is a zero, that a minus bi is also a zero. Okay, so those come in pairs, and I think that's that's the main part. Yeah. Also, here I'm going to flip back to a lesson we did back on Monday, right? And okay, so this goes back a few days ago. You guys remember rational zeros theorem? So if you have a big old polynomial and you say, huh, I wonder where are some good places to start looking for x-intercepts. Right? So this crazy looking polynomial. You can take the factors of this last term, which is 15, or sorry, 16. So what goes into 16? It would be plus or minus. Huh?
1 whole.
Yeah, 1, 2, 4, 8, and 16. Yeah, so all those, plus or minus. Okay? And then divide by the factors of this leading coefficient, 4. So it'd be what, plus or minus 1, 2, and 4. Right? So you could call it P and Q and then do P over Q and you get this whole list of values. Right? You guys see that? Right. So for example, this 1/4 they maybe got by doing 1 over 4. They could have, right? Something like that. Right? Right. So P over Q gives you this whole list. Notice there's all plus or negative, right? So if I flip back to where I am here, and you're trying to figure out where are the zeros, what you can do is you can create a table. So all your P over Q values, you can try all those. You can test all those as X values, plug them all into the equation. And there's a good chance that one or more of these will show up as 0. So it'll tell you exactly what at least one of the x-intercepts is and possibly more. Okay. So I did some examples of those. See. Yeah. Here we go. Right. So here's one of the examples that I covered. Right, is number 31 was this polynomial. Okay. Now, guys, what's factors of 6? About 1, 2, 3, and 6, right? Which I listed here. And then factors of 1 is just, well, 1, right? And do plus or minus. So it's 1, 2, 3, 4, and then times 2 because they could be positive or negative. That's 8 values that I'm tested for x. So I wrote all those up here from -6 to +6, right? Then I plugged each of those into this original expression, and it turns out I got 3 zeros out of that. Ooh, right? In fact, since this is degree 3, those would be the 3 zeros, wouldn't they? Yeah, right. And then I graphed it. So I said a -3, 0, -2, 0, and a 1, 0. Those are all x-intercepts. I threw in one more coordinate and say, huh, what if I plug in 0 for x? I get -6, so that would also be a coordinate. That's not y coordinate. Okay. And then graphed it. And then I did also check on Desmos, and it looked just like that. Okay. So there you go. That is a rundown of that whole lesson. Okay. So yeah, that's a wrap on that one. Walk around and help you guys out. If you want to watch the full video, if you want to hop on Alex, whatever best use of your time, and I can walk around and help you guys out.